Hello everyone. So my name is Ken Liu from ARM. Today I will introduce the TZMP1 software reference implementation on our ARM platform. So here's the content. So first, it is a general process of DRM. First, we have DRM protocols to do the overriding and the key exchange to negotiate our section key for encrypt and decrypt the media bit streams. So in the center side, there's some encoded content, and will be encrypted with the negotiated key. And then all the bit streams will be transferred by networking. And in the receiver side, we will use the key to decrypt it and decode it and display it into the monitor. So the device side, here is the window pass. So because our device uses some popular non-secure OS, so they did not have many security consideration on the protecting something. So the window pass have the risks for the content leakage. So we need to secure the window pass. So the ideal model where secure window pass is we put everything in a secured environment. We put the key and decryption and decoding and compensation in the secure environment. And finally display to the display device. So now the content, okay. So here's a short summary of the ARM TrustZone. So ARM TrustZone is a hardware isolated execution environment on each core. It isolates the CPU in two worlds, non-secure world and secure world. So here's a regular design with TrustZone. First, we receive the packet from the network into the non-secure world because we need the networking stacks running in the non-secure world, and then we decrypt it in the secure world. We decrypt it into the encoded bit streams, and we use the decoder to decode it. And finally, we do the composition in the secure world because secure world can access both non-secure world memory and secure world memory. So finally, display it. So the issues of our regular design is first the issue is the porting because we have much multimedia frameworks in non-secure OS, such as in Android. We have many things. We have OMX, we have GStream, maybe FMPEG, everything. And in our secure OS, we lack of the API for these multimedia works. And the another thing is the runtime problems. Because software needs many status of the media when multimedia works, when multimedia framework is working. So he may need to call many APIs to know the status. It causes many switchings or something. And if we put everything, put the drivers, put the decode, put everything into the secure OS, we increase the many attacking phases of secure OS. So since everything is the encrypted bit stream, decrypted bit stream, and decoded content, we put everything in memory. So if we make the memory accessing a single into a single direction accessing. So could we protect the content in the non-secure world to avoid so much change? So here comes our TZMP1 solution. And here is the overall process, how the TZMP1 works like. First, for non-secure bit stream, non-secure bit stream could only be accessed by non-secure hardware components. And the non-secure VPU could read-write the bit stream, and the GPU could read-write the bit stream. And for a secure bit stream could only be accessed by protected hardware components. If it is encrypted, we have a decrypt to read only it, and write only to the protected memory. And a protected VPU and a protected GPU could do the read-write operations on the protected memory. And display controller, because display controller needs to cite maybe both types of the bit streams. So it could read only from both types of memory, and finally display on the monitor. So the non-secure hardware components includes the CPU. CPU could not access the protected memory, and the more important thing is the protected VPU and the protected GPU cannot access the non-secure memory. This to ensure that there was protected GPU and VPU do not have the chance to write something to the non-secure memory and cause the content leakage. And here we mention the word protected. The protected here means that we wanted to secure something in a non-secure memory. So here we use the word protected to make the difference with the traditional secure memory and the non-secure memory. And all the hardware components access the protected memory conditionally it was added with prefix protected. So here we got a protected VPU and a protected GPU. So this is a overall process we required. And then here comes the hardware architecture to the TZMP1. We have many hardware components connected with some interconnect, and each component was assigned with an NSID. It is it means the non-secure access ID. Okay, so here we see that GPU has two NSID. One is protected for accessing the protected surface or something. Another is the IE, means that it is working as a generic peripheral devices. And the VPU got more NSIDs because our Mali VPU is designed with running with the firmware. So when it accesses the firmware and all the firmware related things such as the patch tables or the intermediate buffers, it needs to access the memory with a private ID. And then if it changes to decode the protected bit streams, it will use the protected NSID. And when it output the decoded result into some surface, some protected surface or some protected memory, so it will use the output buffer NSID. So for the generic accessing, it will, for example, it decodes a generic video in a gallery, or it is just a clear bit stream. They just use the IE NSID. So for display only got one NSID. So the NSID would be checked by the TDD400, and TZD400 will decide the memory accessing would it be legit or be accepted. So here we introduce our firewall over accessing ARM TrustZone controller 400. Totally, it has 8 regions. For each region, you can set a memory range. From which place, from the start position to the end position, you allow which components to read or write, or read only, write only, or read write, or just no read and no write to the memory. And it will check the secure access too. For all the non-secure hardware components, it checks the NSID. And for the secure accessing, it's just checking the secure signal, because as you know, there's a secure signal in our TrustZone design. So here comes the reference implementation. The left side is our hardware. It's a Juno with 2 logic tile. And we take Android and 4.4 kernel as the non-secure OS. The secure OS is OptOS. And other things such as bootloader, long code, ARMTF, and media IPs running in the logic tile. The logic tile is here is for holding the media IP. So it's we 550, G71, and DP650, and the DRM. We implemented the 2 DRM skins, clear key and water wine on this platform. And here is the overall reference implementation on Android. And on the top, we use the Exo player to test the Playback. And then in Android, we have media framework and the Spring. So, for the encrypted stream, first it is received in the non-secure memory, as you know, because we have network things, TCP/IP, everything in the non-secure words. And then the crypto TA, we call the crypto CA to decrypt it. Put the decrypted result in the particular memory. And then VPU access the memory with the NSID protected. To put the decoded result into the decoded memory, and the GPU access the decoded memory, and DPU finally display it into the device. And this is generally a clear bit stream. So VPU just access the memory with the IE NSID. So that's the GPU and the DPU. So here is a modification we required to implement TZMP1 solution. So first, the crypto CA, most of the DRM skins needs the OEM to implement the crypto, such as we have the OEM crypto for waterline something. And we have some changes in OptOS. Actually, in OptOS, it's not a critical function change, okay? And crypto, we need a crypto TA, SGR TA, SGR CA, and the OMX decoder skill, dialog change, iron change, and drive change. We does not mention the hardware change here because hardware is already supported this mode. Okay. So since we need to set up memory regions and set up the memory accessing permissions for TZD400, here's the memory regions we defined and how it is mapped in both non-secure OS and secure OS. First, we focused on the middle about the memory regions. we have 6 memory regions here, and we map the for the first part, non-secure memory is the general non-secure memory. We just leave the Linux to manage it, and for the secure firmware and secure bloodstream, because we have TA running OptiOS to access it, so we mapped it as iron unmapped heap. Unmapped heap is heap means that you can unlock the memory from this area, but you never cannot access it. It is protected by the TZMP. And okay, so, and then the iron carve out for the decoded content, and then we follow the TE parameter. TE parameter memory is accessed by both sides for sharing for passing the parameters. And in the Opti side, we mapped the secure firmware and secure bloodstream part as a secure data bus and everything. The red cross means that it cannot access. So, because our VPUs work with the firmware, we have a secure firmware loading process with the secure gadget library TA. It's similar as the decrypted. First, the secure firmware because secure firmware is stored in the file system. We just load it and decrypt it into the protect memory. And the DRM Crypto is similar with the firmware loading. Encrypted bitstream is decrypted by the crypto with the crypto TA in OptiOS. And the secure decoder. Secure decoder, actually Android has already have support for the security path. So the overall process is the DRM plugin will tell the media framework it needs a secure codec or not. And if it tells the media framework it needs, then the media framework will search for the secure codec in the system. And if it found it, it will set up the security path. First, it will init your secure codec. And then it will apply the flag to the protect surface to be aligned with the codec, because you need to put the decoded content into the protect surface. And for the graphic and display things, it works much more easier because our GPU and VPU support the protected mode for quite a long time ago. So we just adopt some changes in the iron and with the Jalok modules and the GPU SDKs, and then the content is displayed in the screen. So here's the reference for the source code and connect to the community pages. Some of the patches are upstreaming, and some of them are finished upstreaming, and some of them are in the in patches making process. So after all the source code is getting done, we will have a ARM connected to the community page, planned to be done about April maybe. Okay. So this is all. So any questions? Hello?
Hi. For the TrustZone controller, how are overlapping regions handled? Does the hardware raise exceptions? Hello, sorry. For the TrustZone controller, how does it make sure that regions don't overlap? And if they do, how's that handled?
Let me explain. So TDD400, the only region could be overlapped is region 0, because region 0 does not have the setting for the ranges. It just takes all the memory, right? So region 0 is the default setting for all the memory. Then the rest regions from 1 to 7 are not allowed to be overlapped.
Yeah.
Yeah.
When you say they're not allowed to be overlapped, they're configurable, right?
Yeah.
So you can put any value, any range can go into any region, right?
Yeah.
So is it down to the driver to make sure that you don't write an invalid value, or does the hardware do checks to make sure that overlapping doesn't occur? And if so, how does it handle that?
Actually, you need to decide the values before you while you're running the code and while you decide the design, right?
But this is runtime programmable, right?
Actually, so you mean that if there's some regions overlapped, what will happen, right?
Yeah, does the hardware raise an exception, and do you go into a secure exception handler to notify whoever programmed it, malicious or not, that, hey, these regions are overlapping? Sorry?
No.
So the TrustZone controller is not runtime programmed.
Yeah.
It's boot time. So you do it.
But boot time is runtime, right?
Yeah, but the idea is that you do it before you go into non-secure mode, so you would.
Yeah, so it's more like what happens if you've done something wrong in, say,
Yeah,
with
a
startup.
bug. I don't know what would happen in case of a bug, but you know, it's the idea is that you do it only in secure mode before any malicious code would be able to come in as non-secure.
So basically, all the TZC programming is done on the RMTF side. So when actually the board boots up, we set the region on which we set the regions which can be accessed and which cannot be accessed. So yes, I mean it is kind of a runtime, but we set up at the boot time itself. So we fix
Boot time is
those
runtime.
violations.
No, I see what you mean. It's done in
Yeah.
secure mode, but
Yeah.
is there, so there's no well-defined exception handling for overlapping regions. It's not like the TrustZone controller would emit you a particular, like,
So if you
bus
were
error
accessing
IRQ or whatever.
if you're accessing a protected one, which the NSA fixed it will definitely raise an exception.
No, for sure. So that's non-permitted access, right? That would be like a data abort or something. But there's nothing specifically for when you program the device that it would raise you an exception if it detects overlapping ranges. It doesn't check for that.
No.
Okay.
One question?
The changes you've done for the protected surfaces on the secure KDAC side, is that going to be part of the code that you release?
So you mean protective? You mean the GPU part or something?
Yeah.
Actually,
You said you changed
Yeah.
that area to allocate the buffer from ION, etc.
actually,
Is that
they.
in source or in
Uh,
binary?
So you're caring about the how we did that, right?
Yeah.
No. Okay.
Yeah.
No. But since the Mali is itself is a closed source right now, so the changes that we have done is basically the part of the user space drivers, which is not open source, but the reference implementation which we are giving will give the binaries for that. So it is expected that whoever is interested will contact ARM, and then we give out those source codes for that.
Yeah.
Yeah.
Okay. Okay.
You said you decode clear and decrypt video into two different regions. That means you need to duplicate the memory location.
Sorry.
You decrypt, you decode
Yeah.
the video in
Yeah.
clear and in encrypted content coming from secure and non-secure in two different buffers.
Yes.
One secure, one not secure. That means you did twice the memory. If you want to decode the 4K streams, you did the memory allocated, not protected, and then you did the same amount of memory allocated in secure. So you did twice the amount of memory comparing to a non-secure system.
Yeah, that's right. I mean, that's the limitation of TZMP1 is that basically the memory we require is kind of because we have to support both non-secure
Yes.
and secure stream. So obviously the regions are reserved
In
in the
advance.
system.
Yeah.
So that's
Okay.
So no more question? Lucky. Okay. Thank you.